Hello and welcome to Special Relativity. A few lessons ago I presented a couple of paradoxes. Now it's time to solve them. Assume you have a 5-meter long car traveling at 60% the speed of light towards a 4-meter long open garage. From the point of view of the garage, the car is length contracted to 4 meters and it can fit inside. To make sure it fits, right when it's inside, 2 instantaneous laser beams are fired from the ends of the garage. As the car is inside the garage, the laser beam do not hit the car. From the point of view of the car, the garage is the one moving towards the car. So the garage is length contracted to 3.2 meters. Because the car doesn't fit in the garage, the laser beams hit the car and the driver. Does the laser hit the car? Does it not? Well, let's go by parts. When I presented the paradox from the garage reference frame, I said that both laser beams were fired when the car was inside the garage. Because the contracted car is 4 meters and the garage is 4 meters, well, both beams are fired simultaneously. But we have learned that simultaneously is not an absolute. We know that events simultaneous in one reference frame are not simultaneous in another reference frame. Remember the leading light? If we define the 2 laser beams as 2 events A and B, let's go to the car's reference frame. Event A is ahead in space, so it will be happening later in time. From that frame, the back of the garage arrives at the front of the 5-meter car first. Then we have that the garage moves. Then the front of the garage arrives at the back of the car right when the second beam fires. Let's say this with a space-time diagram. So these are the axes from the garage point of view, CT and X, and these 2 red lines are the front and the back of the car. So this we will get as the T prime axis from the car, and the car is moving to the right. This is the contracted length, which is 4 meters. This from here to that point A should be the 5 meters from the reference frame of the car. Event A is one of the laser beams and the event B is the other laser beam, and they take place simultaneously in our garage reference frame, but from the reference frame of the moving car, this one takes place at time equals to 0, but this takes place at time before. So first of all, event B takes place, then the car continues moving, and then takes place event B. So the car will be something like here. This will be the car when event B takes place, then the car continues moving up here, and then it takes place event B. So they don't take place simultaneously. This is a different space-time diagram. Here I have in blue CT prime, X prime, which are the axes in the car reference frame, and these 2 black lines are the world lines of the garage. So this is CT and X going to the left in this case. Now this distance here from one end to the other of the garage, as seen from the car's reference frame, which is in where we are now, is 3.2 meters. The length of the car is this, which is going to be those 5 meters. Now from this reference frame, what we have is that the event that takes place on the right hand side of all this exit problem that we have, this is going to be event B, which takes place before, and then we have A, and this A and that B should be simultaneous from the reference frame of the garage. So if we continue this line, so this is the x-axis, and we see that both events are simultaneous in the garage reference frame. Let's do the math now. For what we assume that events A and B take place at 0 hours in the garage frame, so let's transform this to the car's reference frame. So these are the initial conditions: x prime a equals to 0, then the time a and a prime are 0, the coordinates of b are 4 meters. So remember that we have that the car is here and the garage is here. So this is what we call event B, and this is what we call event A when the car is right inside of the garage. And then we have that the TV, both events take place from the garage point of view at the same time, but this one takes place 13 nanoseconds, which is those 4 meters. Now what I'm going to do is just go and transform that and see from the car's reference frame, I'm going to find xb prime and tb prime. So xb prime is just using the Lorentz transformation equations. It's gamma x minus beta t. This is written in relativistic units. Gamma, remember that we have beta equals to 0.6. For that, gamma is 1.25. Gamma b xb is those 13 is going to be xb minus tb 0, so this is gamma xb, which if we substitute, its gamma is 1.25, and xb 4 meters. 1.25 times 4 meters are the 5 meters, so that makes sense. It happens right at the other end of the car, and because in the car's reference frame the car is not contracted, that has to be 5 meters. Let's have a look at the t prime b, which is gamma, then tb minus beta xb. Here tb is 0. This is negative gamma beta x sub b. Gamma is 1.25, beta is 0.6, and x sub b are those 4 meters, or I will write that in nanoseconds because I'm interested in time now. So add those 13 nanoseconds, and we get 10 nanoseconds, so negative 10 nanoseconds. So this event B from their car's reference frame takes place 10 nanoseconds earlier. Let's see what's the distance that the car can travel in those 10 nanoseconds. So the distance is velocity multiplied by time. The velocity is that 0.6 multiplied by those 10 nanoseconds, and that is 6 nanoseconds, which is 1.8 meters. So remember that the contracted length was 3.2 meters. Now this distance is 1.8 meters. One plus the other is those 5 meters. So everything makes sense. So if we take into account everything we learned from special relativity, there is no paradox. Nothing is wrong with relativity, only assumptions that we make that we shouldn't. So think four-dimensional in the end. May the science be with you.